So notice that if we have the sine of x functions and we have that f prime is representing the slope of the tangent line, when we have that f prime is increasing and the slope of tangent line increase as x increase, we have a behavior of the function being concave up. When we have that f prime decreases and the slope of tangent lines decreases as x increases, then it means that we have a concave down situation. So notice the change in the tangent line. So this is a change in tangent line from being negative to being positive. So if there is a change of tangent lines from being negative to positive, we might be thinking into a concave up situation. If we check and see that the tangent lines are going from being positive to being negative, then we have a concave down situation. So with that, let's define what we mean by this. So concavity and inflection. So if we have a f differentiable in an open interval I, and f prime is increasing on I, then f is going to be concave up. If f prime is decreasing on I, then f is going to be concave down on I. So if f is continuous at C and changes concavity at C, we say that we have an inflection point. So the points where the function is changing from being concave up to concave down, we have an inflection point. And similarly, if it changes from being concave down to concave up. Now, how to test for concavity? So checking tangent lines is not ideal. So what we're going to do is, instead, we're going to use the second derivative for that. So if f prime exists in an open interval I, then we're going to check with the second derivative. And if the second derivative is positive on I, it means that f is concave up on I. And if f2 prime is negative on I, then we have that f is concave down on I. Looking at the sign of the second derivative is much more easier than just checking tangent lines and how they change. And this is very similar to the criteria of the first derivative, where we're using this to check increasing and decreasing. So you probably will know the way that we're going to go with this. Now consider some of the cases. So let's check about inflection points in that situation. So we have this function here, and notice that we have this point where the tangent line was flat, and normally we didn't have anything going on in there, but now we can actually assign a type of behavior for this type of behavior where the function is where this might be a critical point. But it's not a extrema, then what's going to happen is that likely is an inflection point. And you can see that going on in here. We have that f2 prime of C is equal to 0, and also this is a point where we have a flat slope. Notice that in those points there is a change in concavity. So this function was concave down. It was opening in this way, I guess. Concave down, and it switches to be concave up, so something like this. Now the extremas by definition are not going to be an inflection point. So this situation where it's concave up, even if the second derivative is 0, just because this is going to be an extrema, then we know that this is a minimum and we're not going to have an inflection point. Notice that it is a minimum, so everything is concave up in there, as it makes sense. The function is first decreasing and then increases. So notice no inflection point, although you might have second derivative 0 in there. Now, again, we can also have the case where the derivative is not going to exist, and that means f prime of C does not exist, or notice here we have a tangent line that is infinity. In that case, notice that we also not going to have that the second derivative exists. So if the first derivative does not exist, by conclusion, the second derivative is not going to exist in there. This is an inflection point because there is a change in concavity. Notice that this is concave up and then it changes to be concave down. So it is an inflection point. And we also have the situation where we can have a peak. In that case, there's no change of concavity, so look, it's something like this. It's going to be concave down, and then it continues being concave down. We have a peak in there. It's not an inflection point. There's no change in concavity. So remember, inflection points are changes in concavity, as in the same way that critical points, there are likely a change. They might signal a change between being increasing to decreasing or vice versa. It might not always happen, but with the definition of the critical points. But in here we have something similar. So if we want to check when something is an inflection point, we should look for points where the second derivative is 0 or the second derivative does not exist. It's not always going to mean inflection point. Inflection points are changes in concavity, but that's the way that we can look for them. So let's take a look at some examples of concavity and the monotony of the functions. So we can have a situation where the function is increasing and is concave up, but you can also have the situation where the function is increasing and is concave down. So it's not like if it's increasing, then it's going to be something else in concavity. No, we can have both behaviors. Similarly, we can have the same thing for decreasing. It can be decreasing and concave up, decreasing and concave down. Now, let's work with an example. So let's consider a function so that the second derivative is going to have this behavior. We have f2 prime is 12x minus 1 times 2 3x plus 1. So the first thing is we're going to look for those inflection points. Notice that we have zeros, second derivative zeros here at x equals 1 and x equals minus 1/3. Now, what we do is exactly the same thing that we did with the first derivative. We're going to check for the behavior of the sign of the second derivative now. And so we can check with some points. Notice that if we go from minus infinity to minus 1/3, checking that sign is going to give me that the second derivative is positive. Then after that, from minus 1/3 to 1, the second derivative is negative. One example of this can be taking 0. If you plug 0 in here, we're going to get a negative number. And if you go from 1 to infinity and you plug any number, let's say 2, we're going to get again another positive value. And so we have second derivative positive here, change to negative, change to positive. So this means there are changes in concavity at minus 1/3 and 1. So these are inflection points. In this interval from minus infinity to minus 1/3, the concavity is up. From minus 1/3 to 1, the concavity is down. And then again, from 1 to infinity, the concavity is up. Let's see the graph of that function reflected here. So we have the function f of x in here, which is going to be the reflection of this f of 2. Notice that this is a quadratic function that we're drawing in here, and this is coming in 1 and minus 1/3. Notice that is positive outside of after 1 and before minus 1/3, and that is reflected by the signs here, of course, in that function, and is negative between minus 1/3 and 1. So graphing this quadratic equation is going to give you a lot of good perspective on the signs. So now notice since the second derivative is positive from minus infinity to minus 1/3, you can see that the concavity of the function is concave up to that point. Then it's going to change to concave down since f2 prime is negative in there, and then it's going to change again in 1 to be concave up, since the function is second derivative function is positive in here. Now you can also check that with functions like sine to the minus 1 of x. So if you take the derivative of sine to minus 1 of x, there you're going to see that you can have inflection point. And so let's take a look at that on the board. So if f of x is sine to the minus 1 of x, then f prime of x is 1 over 1 minus x squared. And this is the first derivative. Now the second derivative will be considering the derivative of this. This is a chain rule, so the easiest way that I can do this is just write that as a root with negative powers. So then the second derivative is going to be minus 1/2, 1 minus x squared to the minus 3/2, and multiply by the chain rule, which is going to be minus 2x. So now the 2 gets to cancel with the 2 and the minus with the minus, and we get to have x over 1 minus x squared to the 3/2. So this is the second derivative function. Now once that we're here, what we're going to do is find the possible points where f of 2 prime is 0 or f2 prime of x do not exist. And so clearly f2 prime of x equals 0 is going to happen at x equals 0. And f2 prime of x do not exist is going to happen here where 1 minus x squared is going to be 0. So that happens at x equals minus 1 and x equals 1. So we have those if possible inflection points. Now from there, what we got to check, of course, is the intervals. Now we don't necessarily going to use all these points. It depends on the domain, right? So in a particular case here, we're just going from minus 1 to 1. So we're kind of in the edge with what we're getting. We're not going to take points where the derivative does not exist, since those are being taken out by the domain. So we don't really need to consider what's going on in here. And we can just use this part and this part to check the sign. So we can just check with minus 0.5 and 0.5 what is the situation. If we do f2 prime of 0.5 or 1/2, this is 0.5, and over here is going to be 1 minus 1 over 4 to the 3/2. So as you can see, this is positive. And when I do f2 prime of minus 0.5, we're going to have a similar situation, but it's minus 0.5, 1 minus 1 over 4 to the 3/2. So that's going to be negative. So here we have f2 prime is negative. Here we have f2 prime is positive. And so here this is saying, hey, concave down. This is saying concave up. Okay? That's just the information about concavity. But everything else is, notice, concave up, concave down, as expected, from the sine to the minus 1. And we have that there is a change in 0, so we have that this is an inflection point. Now, let's summarize also the second derivative and his behavior to give you information about maximums and minimums. Notice that for obvious reasons, when we're talking about concavity, we tend to say, well, it might have this behavior, it might have this behavior. So if we are talking about a critical point, this might tell me what's going on around the critical point right away. The concavity is going to tell me, okay, it's concave up, it's concave down around that critical point. Careful, not the inflection point, critical point. And so if it happens at concave down in a critical point, then we know that that is maximum. If we have a concave up in a critical point, then we know that that's a minimum. So that's the situations that we have here, and that's exactly what we're going to conclude here. So if f2 prime is positive, so concave up, we have a local minimum. If f2 prime is negative, concave down, then we have a local maximum. Remember, f prime of c is a critical point. Okay, we're talking about this critical point. Now, when f2 prime of c is equal 0, this test is going to be inconclusive. That means that the critical point might be an inflection point, or is an inflection point, and we might have a local maximum, a minimum, or neither. But we gotta check for other means. Okay, so let's see what that means in terms of again the concavity. We have a critical point, slope is flat over here in the function, and notice that f2 prime at the point c is bigger than 0, and it's indicating that it's concave up. So this is the situation. We have a local minimum. Let's check another example here. We see this function. In this function, we have that 1 is going to be not a local stream, but it's going to be a change of inflection. We have concavity down here coming and changing to be concavity up. So this is a change of inflection. It's an inflection point. And over here on this one, though, we have a flat slope. It's a critical point, and it's changing from being decreasing to being increasing. And also is when you check the second derivative is positive, which reflect that this is concave up. So we do have a minimum in here. We can check also the type of behavior in functions like sine square of x. Just remember that sine square of x by trigonometry is just a transformation. Is just a transformation of a cosine function. It's a cosine function that is being shifted and moved up. And what I mean by that, let me very quickly remind you. That you have sine square of x. This can be represented as 1/2 plus cosine of 2x over 2. And so this is essentially a cosine that has a shift in the period. Is now is completing his full period in from 0 to pi. And now it's being divided by 1/2, so it means that the scale is just 1/2. It goes from -1/2 to 1/2, but then we're going to move that 1/2, and so now we can go from 0 to 1. Okay? And so that's precisely this function that we have over here. We're flipping, sorry, this has a minus over here. It's not a plus. It's a minus. Okay, that's just trigonometric identities. Then here with this, notice that if we take the function sine square of x, the first derivative is going to be 2 sine of x cosine of x, and we can take the second derivative as well and make some calculations. Notice that we're going to have that the slopes are flat in pi, and pi half, and 0, and so on. So in all those points, we're gonna check what's going on. Those are critical points. Notice around this is f2 prime is being positive, so local minimum. Here f2 prime is negative, local maximum. f2 prime positive, local minimum. f2 prime negative, local maximum, and so on. So you can always check very quickly if you have a critical point, and you can take the second derivative easily. Then instead of checking what's happening around the critical point, this helps me go very quick and say, yeah, this is a maximum. Yeah, this is a minimum. Okay. So let's actually do that on the board for this example. So I'm not going to go directly with the identity. The identity will make the derivative easier, but let's do this. Y equals sine square of x. So y prime is going to be 2 sine of x cosine of x. that, remember, this is actually sine of 2x, which makes sense, right? If we take derivative of this is 0, derivative of cosine is minus sine, so it gets to be a plus here. And with the 2 that comes out from the chain rule, you get this 2 out. So that's just the first derivative. Second derivative is going to be 2 cosine of 2x. This is easier to check. So now critical points. Critical points are where sine of 2x is equal 0. It's not going to happen that it's not going to exist because sine of x is a function that is defined in all the real numbers. And so now you can see here that is in every multiple of pi half. So sine of 2x is equals 0, x is equals n pi half, where n belongs to the integers. So all of these are possible critical points. Then after that, what we do is we check for what happens with y2 prime. So it obviously is going to depend of what is the n. So for example, this is going to include x equals 0, x equals pi half, x equals pi. So looking for some of these values, you can get information. Y2 prime of 0 is 2 cosine of 0, which is positive. So right away you know that this critical point is going to be a min. Y2 prime of pi half is going to be cosine of 2 cosine of pi, which is going to be minus 2. This is a negative, so this is going to be a maximum. And y2 prime of pi is going to give me 2 pi, so 2 cosine of 2 pi is going to be 2, is positive, and so we're going to have a minimum in there. And so that is exactly the situation that is being reflected here. So notice in pi and 0 is a minimum, and in pi half is a maximum. Now in general, we can have a lot of behaviors that can happen, and there's going to be useful for graphing functions, and this is going to be part of what we're going to go into details on section 4.4. But we have that if a function is differentiable and is smooth, then f prime positive means that it's increasing, f prime being negative means that the function is decreasing, and the changes in signs of the first derivative implies that you have a local maximum or local minimum. Notice this type of change from positive to negative in f prime or negative to positive are going to give me either maximums or minimums. But we can also check that with the second derivative. If we have a critical point and we check what happens at that critical point, we either have a local maximum or a local minimum. And in general, if we're not stepping in a critical point, if the function is, if second derivative is positive, then you know that the concavity is up. If the second derivative is negative, then you have the concavity is down. And any change on the concavity means that we have an inflection point. Okay, so that's the summary of section 4.3.